The next presentation will be delivered by Teng. He is a senior engineer from Alibaba Group, and he will tell us about PLOCSCHED that supports efficient live updates of the Linux kernel scheduler. So if you're ready, then please take it away.
Okay. Hello, I'm Teng from Alibaba Group. Today I will present this work, efficient scheduler live update for Linux kernel with modularization. So first off, the default Linux scheduler is one of the basic and complex subsystems in the kernel. It's tightly coupled with the structures and functionalities of the kernel. While the default Linux scheduler is powerful, the applications often require different schedulers to achieve the best performance. For instance, microsecond level workloads like mem cache, silo are extremely sensitive to scheduler overhead. The scheduler is designed to be applicable for different scenarios such as mobile, HPC, desktop, because there is no one-fit-all scheduler. So the cloud service providers must allow users to customize the scheduler. To update the scheduler, the developers should reboot the OS by multiple steps, and the whole process can last from a few minutes to a couple of hours. It will become a disaster for the latency-sensitive online applications. Most live patch tools are function-level solutions. They are general tools in Linux servers. They focus on handling small security patches with very few code changes. Some works also support the component-level live update. Prot OS relied on the characteristics of microkernel OS, which means it wouldn't be general for Linux servers. Also, it's enabled live update of KVM, so do KVM, because KVM is an independent kernel module. VM PHU depends on the virtual machine manager. It is only suitable to update the guest kernel in virtual machines. In Ghost, the scope of the live update is limited to the scheduler class, and the actual communication overhead between user space and the kernel space, such as context switch, increases the end-to-end latency. In our design, we should consider three constraints. First, it shouldn't incur kernel code changes. Second, it should be able to be deployed in Linux servers. And third, it shouldn't be only available in the virtualization environment. Thus, we have four goals to achieve. Expressiveness means supporting component-level live update. High generality means without actual constraints such as microkernel of VM and so on. At the same time, achieve both short downtime and safety, and easy to use. It should be easy to use for the development. This figure is a big graph of PLOCSCHED. In the pre-processing phase, PLOCSCHED automatically gathers the scheduler relevant information such as the symbols of functions and the data during the compilation phase. Then it runs the boundary analysis algorithm to determine the clear boundary between scheduler and the kernel, and divides functions into three types: internal, interface, and external functions. In the code extraction phase, it reorganizes the scheduler relevant code to a separate directory, and the scheduler is decoupled to a new module. In the development phase, the developers can freely develop the scheduler, and then generates an RPM package in the development phase. PlugSquid should find a safe opportunity to replace the original scheduler. Then PlugSquid uses stake inspection to examine all kernel stakes and check whether they are unsafe threads. After that, PlugSquid replaces the preload instructions of original functions to redirect to the new function. At the same time, PlugSquid migrates the data from the older scheduler to the new one to guarantee its up-to-date through data rebuilding. We propose the boundary should be function granularity. Accordingly, we divide functions into 3 types. The function set of scheduler module is a combination of interface and internal functions. Typically, a calling relationship is from external to internal, and then to external to interface, and then to internal functions. Boundaries obey 3 rules. First, easy to maintain. The developers just need to maintain the set of interface functions and the internal data. The boundaries should be convergent, and the scheduler is a closure, which means the kernel can only interact with scheduler through interface functions. As shown in the left algorithm, in the left, PlugSquid loads configurations including interface functions, all functions in the scheduler files and the kernel call graph, and then it travels all call relations in the call graph, then call E is added to the external functions if the caller fulfills the conditions. The loop ends in the case of no new call E adding to external functions. Then the boundary of scheduler is clear. Before upgrade the scheduler, PlugSquid needs to check the call stack of all threads to see if any thread still falls within the text of older functions. PlugSquid uses stop machine to stop all CPU calls, so only the specified CPU is allowed to execute the user-defined handler, and the rest of the CPU calls are halting. PlugSquid obtains the start address and the length of every interface functions and sorts them by the start address. Then PlugSquid uses binary searching to speed up the comparison. Since stack checking is independent between threads, PlugSquid divides all threads into C groups equally and assigns groups to cores one by one. Each core checks the safety of all threads within its group. After that, the kernel is in a safe state, and all threads are stored. Therefore, PlugSquid replaces the preload instruction of original functions with the jump instruction. PlugSquid disables the page protection mode to allow writing into the code segment during the function redirection. The only exception of function redirection is the scheduler function. A scheduler function not only implements the algorithm that selects the next running task, but also executes a context switch. So PlugSquid splits a scheduler into a modifiable part and a read-only part at the point where it invokes the context switch. To avoid a stack corruption, stack pivot is used to adjust the stack frame size of the new scheduler function. To control CPU execution flow, return address of context switch is modified to the lower part by using ROP. Plug-skewed divides the data into the external and internal according to usage scope and adopts different strategies as shown in the right table, inspired by the state's migration processing in resetting the scheduling policy. Plug-skewed follows the three main principles of rebuilding to construct a state in new scheduler. Firstly, we observe that in-queue task and D-queue task are stable APIs in scheduler, and every schedule class, such as the CFS, must implement these two callback functions. Secondly, because all scheduling features or policies are applied to tasks. Finally, in-queue task and D-queue task are critical paths in these implementations. Thirdly, the state of run queue is built by in-queue tasks one by one and is clearly by DQ tasks one by one. There are several constraints for developers, such as not supporting changing the size of data structure and modifying the semantics of each original field, and support cascade left update. So we have implemented plug-skewed on both Intel and ARM. It contains 2 kilo lines of Python code and 6 kilo lines of C code. We perform most of the evaluations with several bare metal servers, as shown in the right configurations. To show the expressiveness of plug-skewed, we use 4 random selected Linux upstream patches and 3 new scheduler. Overall, the downtime is between 2.1 millisecond and 2.6 millisecond for the install with an average of 2.4 millisecond. We also compare plug-skewed with K-patch with the install and uninstall. In the stack inspection phase, plug-skewed is 12 times more efficient than K-patch. The left figure shows the per-core processing throughput of Nginx when we update the scheduler with plug-skewed. In the upper part, all the 96 cores are used by Nginx. Plug-skewed starts to update the scheduler at the time at this point, and the update ends at the time 1.6 seconds in the upper part. In the worst case, the core throughput drops by 36%, but only lasts for only 4 milliseconds. And even under several heavy workloads, there are sysbench and hackbench. The downtime increases at most 61%. In plug-skewed, multiple cores can be used to speed up the state inspection during the scheduler leaf update. Stack inspection time reduced from 1287 milliseconds to 282 milliseconds when the core number increases from 1 to 96. And the stack inspection time reduces by 85% with 24 cores. And as a summary, as shown in this table, we conclude the potential solutions and make a comparison between plug-skewed and other works. Plug-skewed supports a component-level update safely without incurring kernel changes or actual overhead, and of course it has good expressiveness and generality. Okay, so finally, our work is already open source. This is my talk. Thank you all.
Thank you.